I've hit the start stream button, which means hopefully the stream started. We are roughly back at it again in whatever, what did I call this series? I think computing from scratch or something. Let's make sure that we're live. We are continuing where we left off last week. We're live streaming at approximately the same time. Maybe I'll just keep this pace going of it once a week on Wednesdays or something. Let's see here. I hit start streaming and oh, there we go. I see it now on my phone. The audio. Okay. Let's see here. I hit. So that is working. I changed up the audio settings like slightly or something in OBS. So if they're worse, hopefully not, because I did pay attention to how I changed them. But if they're worse, please say something. Or if anything about this streaming setup is bad, or video quality is bad in some way that I'm not thinking of, please let me know so that I can get that corrected as soon as possible. Okay, so I see a couple of viewers have trickled in. Let's see here. Where did we leave off on the previous video? Oh boy, I see this audio thing going into red sometimes. Mildly terrifying, but hopefully it's still good. It's gonna be good, guys. Someone will tell me if it's not. All right, where did we leave off last week? So we left off last week writing this bootloader.asm. So our goal right now is a whole bunch of things. We want to explore learning a new concept. So something on pwn.college that we don't really do all that often is, record things from the perspective of us trying to learn something, kind of document the learning process a little bit. So hopefully that's kind of interesting for people. And in particular, what I am diving into in this series is looking at some low-level stuff. So I'm very comfortable with the Linux kernel existing as kind of my base layer of abstraction, and everything builds on top of that. You do syscalls to the Linux kernel, etc., etc. You get things to happen. I'm trying to go one layer lower, get closer to the hardware, and kind of the natural spot that I wanted to look at to do that is looking at the bootloader. Which allows us, we just got some raw bytes sitting on a disk getting executed. I guess sitting in memory. Somehow they make their way from the disk to memory. I don't know how that happens. I think the BIOS, if I had to guess, maybe scans the hardware, looks for a hard drive or something, looks for this little boot signature thing on a sector within the hard drive, and then just copies the 512 bytes into memory at this address. And now we've told NASM, or I think we're using NASM to assemble this, told NASM we want everything to be relative to this address, and then, when it does its thing, it's relative to that address, and hopefully everything just works. That's kind of my impression of how things are working. We haven't really dived into the BIOS. I don't know if we will, go into that or not. For now, we'll just kind of assume that's true until we need to understand that that's maybe not true. It's kind of a working hypothesis, but I don't think it's going to affect us too much. All I know is we got 512 bytes loaded into memory at this address somehow. We're in this 16-bit mode. Actually, I'm going to zoom in even a little bit more. We get this 16-bit mode that that our x86 is in. So normally, we're in protected mode. We got 64-bit x86 running. The CPU actually does not start in that setup. Instead, it starts in 16-bit mode, which means, if you're familiar with like the RAX register, we don't have access to RAX because our CPU is not executing in a 64-bit mode. We're in a 16-bit mode, and we're in real mode, which I think we'll kind of further understand hopefully in this video. I think gives us access to some CPU instructions we might not normally have access to once we switch into protected mode. That's kind of my guess. But we are going to seek to understand some more things of what's going on. So in the last video, as kind of maybe a quick refresher, let's see here. If I can go ahead, we'll make this so we don't care about the host name. Don't know how many terminals we're going to need, but we'll do this for now. Don't worry, password.py is not actually my password. We don't need that though. We've got this boot thing. Yes, okay. So we built out this run.sh thing, which kind of documented our process for ourselves. What it does is it assembles this bootloader.asm that we were showing and then starts QEMU with a drive pointed at these 512 bytes. Bootloader.bin is in fact 512 bytes. And that is what gets loaded in as a drive, and the BIOS takes care of things and things boot. Okay, so let's go ahead and run run.sh, which gets a VNC server running on this port. If I remember right, we needed to run this command as well so that we can see it in our browser. We're emulating everything with QEMU, and we've got VGA going on here, and this VNC, and then further on layer of no VNC allows us to see that monitor. So we needed that, and then we can view it right here, I think. Let's see here. So if I go here, okay, we've got our VGA screen. And in fact, I'm going to, right off the bat, pull this over here. Take this here, put that there, put that there. Actually, maybe we will zoom out a little bit then. And if I type A, let's see, make sure we're focused on the screen. I press A, we can see an A is over there in the bottom. I'm just typing on my keyboard, hitting random letters, and we can see that they appear on screen. And this is what we built out in the last video. It looks like we still have it set up where we add 3000 to DI right away, which is why it's starting in the bottom right and not the top left, because it kind of moved further along into the screen. If we rerun this, reboot the computer, we should see now that if I type, yeah, we're typing right here. So this is what we built out. Pretty cool stuff. So we got this main loop, we get a key, we print the character. We get a key, we print the character. When we get the key, we use this in instruction from, I don't even know what we would call this operand. Let's see, actually. Maybe we'll start with that as our question. Let's switch over to ChatGPT. Looks like we're now on GPT 4.0. We'll see how that affects us. Last week we were on regular 4, but 4.0 just came out. When I use the, in fact, let's zoom in a little bit. Maybe even more. Yeah, okay. When I use the in instruction, what exactly is that 0x64 value? What are the sorts of values that can exist? Explain away the magic value. Let's see if we can understand what the heck this is. Okay, so instruction is the IO port address of the keyboard controller status register. So it is the IO port address, okay? You are reading the status byte from the keyboard controller status register. The status register contains various bits that provide information about the state of the keyboard controller. So bit 0 is the output buffer status. Bit 1 is the input buffer status. Bit 2, I guess this is specifically for this 0x64 status register thing. So we got a system flag, we got command, data, last right. This data was a command. Keyboard is unlocked, keyboard is locked. Auxiliary device output buffer is full, timeout error. Parity error. Okay. So that's kind of, I guess that means, kind of implies that we're getting 1 byte back, which makes sense because it's just going into AL, which is a 1 byte thing. And I believe we're just checking if the whole thing is 0 or not. Let's see here. Yeah, we're just test. Well, no, I guess we're technically testing just that one bit. Check the output buffer status. So in fact, we are checking the correct bit. We're not just checking the whole byte. We're specifically checking this bit 0 with that test AL1, which tells us if the output buffer is empty or the output buffer is full. Which I guess output buffer full just implies data available for reading. So I don't know how big this buffer is. Maybe we could ask, but so we got common IO ports for the 8042 keyboard controller. So this is like, really getting closer to the hardware there. That it just happens to be that, 60 does this and 64 does this. Used to read data from the keyboard controller when the output buffer is full. Used to send data to the keyboard controller when the input buffer is empty. I wonder what it means to write to this thing, right? I think in the past, last week we were writing to memory actually to get things to appear on this screen. I think there's an out instruction. Not sure what context it would make sense to use the out instruction, but that is what we currently got going on here. And let's see here. So that. Okay, cool. I feel like I had another question. What other port addresses are available for things besides the keyboard? Let's see here. We've got a programmable interval timer thing, whatever the heck that is. CMOS RTC, whatever that is. DMA, direct memory access controller. DMA channel. Okay, so these are some concepts I don't really know a lot about. I've used a keyboard before. A programmable interrupt controller. Serial ports. Okay, so this is able to go past hex 100. So it is larger than 1 byte for this address. Okay, we've got some serial ports. Similar layout as COM1. Modern modem. Okay, so somehow probably hardware can get plugged in over a serial port. I think our keyboard is it over a serial port? I don't know. Maybe it is, maybe it's not. We've also got parallel ports. Not really sure what is meant here by serial versus parallel. Obviously, serial means one and then the next and then the next and then the next, whereas parallel means like multiple things at once. But not really sure about what the actual implication of that is here. Oh, here's VGA. Subsequencer. So probably we could draw to the screen over VGA using these ports. Which is kind of cool. I'm not totally sure. Like, I'm imagining I'd use the out instruction and could write to VGA. I wonder what the difference is between like this direct memory access where I'm just literally writing to memory, right? Where we set up this segment here, our ES segment, and that at this address, and then we're just writing to address B801, and then B802, and B803, and B804, all these addresses, 1 byte at a time. Ultimately, we're writing ASCII to that location in memory. It's a 2-byte thing, though, if I remember right. See a print character. Yeah, we put this 0F in the high byte of this 2-byte register. This one being ASCII, this one being like attributes about it, like white text on black background. And then we write to memory. This writes to memory, and also increments so that the next time we write to memory goes to the next place. So maybe there's a way to do it instead through here instead of memory. It seems kind of nice to be able to do it through memory, and that there's some sort of hardware or whatever that's handling the fact that I have ASCII. So I'm imagining, right, like VGA is just like pixels, right? Like probably the hardware at its fundamental level is just coloring pixels. So something is handling ASCII and like rendering this A character when I write to memory in that way. Got a floppy disk controller, a hard disk controller, secondary IDE channel. Okay, so we got a whole bunch of things to interact with hardware. Let's see here. Why does my code write ASCII directly to memory instead of using some sort of out instruction over the VGA ports? Let's see here. Because direct memory access is simpler and more efficient method for text mode display manipulation in the context of early x86 systems, particularly those with BIOS support for text mode, like the 8086 and 8088. Okay. The video memory for the VGA or CGA display starts at this. It's organized character. The first byte represents the ASCII value of the character. The second byte represents the attribute. By writing directly to this memory area, you can control what is displayed on the screen without the need for additional instructions or processing by the video hardware. This is particularly useful. Okay, so we've kind of got this like layer of abstraction that's facilitating this simplicity. I wonder who's providing this abstraction. Direct memory access. Is it the BIOS? And how does that function? I mean, I don't know if I want to go too far down the abstraction hierarchy, but who the heck is doing this? Like is someone reading from memory in a loop, or like what's happening there? From the AX register into the memory location. Like I'm wondering, like, do 100 x86 instructions suddenly fire off after I write to this one location in memory in like response to facilitating this, or how the heck does that work? Why not use? Okay, so obviously it'd be more complexity. Is it even possible? You'd need to select the correct VGA port. You'd need to send multiple commands to configure the VGA hardware. Like I'm wondering, maybe does VGA as a protocol support ASCII text? And it's like the hardware on the VGA is doing it. And if you were to use these out ports, you're just specifying where in memory. Like maybe you're configuring the VGA that the 0xB800 thing, this is the location that VGA should be looking at, or I wonder how that works. You need to manage the cursor position and other settings manually. The out instructions, port IO. Okay. Who facilitates this direct memory abstraction layer? Is it the BIOS? How do things respond to memory being written to? And then in response, doing hardware stuff. Let's see here. VGA, the BIOS is primarily facilitated by the hardware design of early x86 systems. Let's see here. Including VGA hardware itself. The BIOS plays a role in setting up the environment. Okay, how the abstraction layer works. Hardware design. Video hardware in x86, such as VGA, is designed to map a specific... Okay, so maybe it is what I was saying. Like we would use an out instruction to say this address, or maybe it's just always this address. The hardware just always looks at memory at this address. You don't even get to change this address. This... Each byte or pair of bytes written. Okay. The video hardware maps specific memory addresses to screen positions. top left corner of the screen. Okay, I think this really is the hardware that's responding to memory then. And then the BIOS is doing some sort of basic configuration maybe. Let's see here. Also, if anyone throughout this ever has questions or, has questions of their own, feel free to ask and I can, we can further go into that. However, once the system is running, software like your bootloader code can, okay, so I think the BIOS just configures stuff, possibly is configuring that it's this address, possibly not. Maybe that's just hard-coded by the hardware somehow. Initialization, BIOS sets up initial video mode, text mode, graphics mode. BIOS provides interrupt services. So we haven't messed around with like int 10. That's interesting. What these other interrupt services are. So for example, I know in 32-bit x86, when you wanted to make a syscall to Linux, you would do int 80 as like, there was no syscall instruction. It was just you do int 80 and then the kernel responds. So it looks like there's other interrupts that you can facilitate, or they can be facilitated. I don't know who's facilitating these things. I guess the BIOS is. These are not required for direct memory access. Response to memory writes. The CPU writes a value to a specific memory address within the mapped video memory range. Video hardware response. The video hardware continuously scans the video memory to determine what should be displayed on the screen. Maybe the hardware is literally just running a while loop and just like, boom, what should I be drawing nonstop? When the hardware detects a change in the mapped memory region, it updates the display accordingly. All right, so we're going to take that as the hardware really is doing this. I see in chat, I see someone saying, I think that's correct. You're handling the VGA device/card through that interrupt instructions. Yeah. I don't know if we're doing interrupts though. I think like I think it's like, is it like the CPU is pointed at memory and you do a write and it writes to memory, and then the hardware, the VGA monitor is pointed at memory, and both are just pointed at memory. This guy's just constantly looping trying to read that address of memory, and this guy, the CPU might just randomly write to memory. It kind of seems like the layer. I don't know. There might be, it's abstractions all the way down. That might be an abstraction in and of itself. Maybe you write to this address in memory and it doesn't even go to, like a stick of RAM. It literally just goes straight to the display hardware. I really don't know that, but we're not going to go too deep on this. We need to start writing some code soon. But this is interesting. Direct interaction with hardware. Direct memory works as follows. Continuous refresh. The video hardware constantly reads the video memory and refreshes the screen. Alternative? Is this an alternative thing? Hardware mechanism. The hardware includes mechanisms like CRTC, cathode rate. This is like some hardware stuff in VGA, which manages the display refresh, cursor position, and other video output functions. So I think like the monitor literally just knows where the cursor is, and like it's doing its own thing. Let the hardware do hardware things. Abstract away the hardware at least a little bit here. Example, writing to video memory. This. Yeah, we already did this. Okay, cool. All right, I think something about this makes sense. I'm seeing the VGA device checks that specific memory address, which are managed by the CPU. Yeah, okay. I think we agree. Okay, cool. So we've got the ability to do this now, right? We can type to the screen by doing this simple little loop forever. And the functionality, not too bad. We use in to check if there's stuff. If there's not stuff, just loop again. It's just like rapid looping. Possibly we could figure out how to, make it so our CPU isn't just constantly in this rapid loop, just like if we imagine we've only got one core, which I think right now our hardware is configured with one core. What if I want to do other things simultaneously? Do I really want to be busy looping forever? Maybe there's a way to get interrupted instead whenever this occurs, right? Like um, not have to deal with the fact that, we're in this loop forever. Maybe I want to be doing things simultaneously. And, one option would be to just half the time, instead of jumping back here, like go do some work for 100 instructions and then come back. We could imagine setting it up that way, but it'd be nice if like the hardware could be set, like told like, hey, set the instruction pointer here if this ever changes. Like just aggressively divert my control flow on in response to hardware things rather than just busy loop pulling this, right? This works right now because that's the only thing we're trying to do. Okay. Let's see here. Print character in AL at current cursor position in ES to DI. Okay, so we got a few directions of what we could do here. Says knowing the address is affected by an interrupt, you can do something with what the VGA does. Okay, I think I want to see if I can get this interrupted. So here's what I want to do. I want to make it so we have this like an asynchronous mechanism here. If the hardware supports it, there might not be, hardware support for this. I probably need to ask ChatGPT before I assume that there is functionalities for this, but I'm guessing there's some way to set up like interrupt handlers in response to hardware. I'm just kind of vaguely assuming this is a thing that can be done. Could be totally wrong. Actually, let's just ask. Can I, instead of constantly pulling 0x60, I think it'll understand what I mean. 64. Can I instead set up an interrupt handler or something like that to execute code in response to hardware activity? I don't know if my terminology here is totally correct, but hopefully, this is what I'm hoping of ChatGPT in terms of learning, is that ChatGPT will kind of understand my incorrect terminology and respond accurately to it and also tell me some of the terminology. You can set up an interrupt handler to handle keyboard input instead of constantly pulling the status register. This method is more efficient as it allows the CPU to perform other tasks, right? We don't want our computer just only sitting here checking if the keyboard has something going on. Probably instead, we want to do some tasks, and as soon as there is keyboard, let's interrupt and like go deal with that and then go back to our task. Okay, setting up an interrupt handler for keyboard input. Identify the keyboard interrupt. The keyboard typically generates IRQ1. I feel like I've seen this term, IRQ, in the context of Linux. It's like there's like soft IRQs and hard IRQs or something, maybe. I don't know what the heck these things mean, but whatever. Which is mapped to interrupt vector 0x09 in the interrupt descriptor table. Okay. And I don't know what that means, but sure. Generates an IRQ, which is mapped to interrupt vector 0x09 in the interrupt descriptor. Okay. Write the interrupt service routine, ISR. The ISR will be executed when a keyboard interrupt occurs. This ISR will read the scan code from port 0x60. When a keyboard interrupt. Okay, so maybe keyboard interrupts occur for all sorts of things, but then okay, we'll see. What is this? Let's let it roll a little bit. Install the ISR. Replace the default keyboard ISR with your custom ISR by modifying the IDT. Okay, again, these are words that are having limited meaning to me. Enable interrupts. Ensure the CPU and the programmable interrupt controller are configured to allow keyboard interrupts. Okay, this means something to me, which is that the very first thing we did, I think this instruction is disabling interrupts from being possible. So we might need to enable interrupts, or at least some subset of interrupts or something like that. Okay, so this agrees. Disable interrupts. Set up the stack. Oh boy, we're getting a stack going. Why do we need a stack? We're gonna figure that out soon. Okay, we got a whole bunch of code. Let's try and break this apart. So zero out AX, move that into SS, which I think is our stack segment. Move SP, which is like, RSP, but this is presumably the 16-bit variant of it. 7C00, but I thought, why are we, isn't this going to be an issue? This makes me nervous, but we'll pretend it's right for a moment. I'm worried that this is going to somehow have the stack like overwriting my code. Okay, save the original ISR. So push DS, move AX0, move AX DS. Okay, 0x00. Okay, so this is the 9 thing it was talking about. An interrupt. Okay. Original ISR. The heck is this? We have a location in memory somewhere? Original ISR. Yep, somewhere in memory we got this thing. So we're writing there. Okay. And then 9 times 4 plus 2 goes into AXY. 0x009 DS push DS. Wait, this is the data segment, right? DS is the data segment. So we're setting up the stack so that we can temporarily save. Can you add more comments to this code? For example, what is DS? I think it's like the data segment, right? Okay, there we go. Set the stack segment to 0. Yep. Set the stack pointer SP. Okay, so we are putting the stack pointer to the top of the bootloader space. Why? Why do we want the stack to be? That sounds terrifying. Are we going to start overwriting instruction pointer, like instruction bytes? Why not go somewhere else? Okay, push DS. So save the current value of the data segment register. We're doing that because we want to change the data segment. So set AX to 0, address of the interrupt vector table. Okay, so I guess the interrupt vector table just lives at address 0. And specifically, this ISR is at like 9 times 4 or something. So I guess maybe each one of these ISRs is 4 bytes long. And so we're going to the 9th one, right? You could imagine 0 times 4, 1 times 4, 2 times 4. This is the size. This is which one, index in. So we've got these 4-byte values. Probably it's going to be like an instruction pointer or something's going to be going here soon. Okay. So DS to 0 so we can access the IVT, interrupt vector table. So when we talk about null pointers, you're saying the null pointer, the nullest null pointer is the interrupt vector table. So address 0 is literally interrupt vector table. Is this true? It's kind of cool. Load the lower 16 bits of the original ISR address. Okay, so we take the current ISR. Are we about to just try and save this? Yeah, then we save it at orig ISR, right? Which is just somewhere in, memory, not on the stack, just somewhere in memory. store the lower 16 bits. Oh, and then yeah, because we can only do 2 byte copies at a time because I guess 16-bit mode means you get to save 2 bytes at a time. So we got to do, this is a mem copy, right? A 4-byte mem copy. So we're saving the original thing, and then, okay, so now it's been saved. Save the original thing into our memory space, and then we're back to the original, whatever the heck DS was. I wonder what DS is. Do we like, is this, just to be slightly more correct, is DS already pointed at 0 and we don't really need to play this game? Or what? And then we don't even need to set up our stack? Let's see, where is GDB say that we currently are? cd dev cd boots ls clear ls cat run.sh gdb xdebug.gdb info registers. What is DS currently pointed at? Is this lying to me? Is it already 0 and we don't need to do this? I mean, I like being safe, but I'm curious if we need to do all this like saving stuff, or if we don't really care about that because it's already what we think it should be. Either way, we'll roll with it. Okay, install the new, so all we did here was save the original ISR. Yeah, that's what this comment says. Save the original ISR address for interrupt vector 9, keyboard interrupt. Is this like a code address? Is it, what is an ISR address? Is this, let's see. Okay, install the new ISR for interrupt vector 0x09. Disable interrupts again. Why do we have to disable it again? Is it not already just disabled? Did one of these instructions re-enable it? Why do we have to re-disable? Oh boy, we don't need to do that. Why do we need to disable interrupts again while installing the new ISR? Aren't they already disabled? We're gonna ask that. Okay, but let's keep rolling. Install the new ISR. What is this? What the? I don't understand what this is. New ISR. Where the heck is new ISR? But we got a lot of code that we just generated here. New ISR. Okay, so new ISR is just a location in memory that has some instructions. Cool. I don't know why it's prefixed with that, but roll with it for now. Set the segment part of the IVT entry. So we took this location in memory. Oh, I think this is so that it doesn't just pull the first 2 bytes there. I'm familiar with using the term offset when doing, what's it called? Instead of NASM using, I mean, it's basically just the GNU stuff. GAS, that's what it is, GAS. I'm used to using the word offset. I think this is basically the equivalent of offset. It's just give me this actual address. It's probably what that's doing. You put that in AX, set the segment part of the IVT entry. So AX goes at the +2 part of this. Oh, this is offset. Okay, one is the segment versus the offset. So this probably is just taking this, right? The 7C00, it's just like the more abstracted way of saying that. Okay, then we load the actual offset. So this is what I'm familiar with. Yeah, offset, put that AX, put it here. So we just loaded it in backwards, I guess, whatever, that's fine. Okay, this is a new instruction, enable interrupts. Okay, so we've definitely enabled interrupts. But why STI and then STI again? Is this not redundant? I don't understand that. Okay, main loop, halt, new instruction. I think I've seen this instruction. Halt the CPU until the next interrupt. Does this actually save power? Cool. I mean, if not, it's at least just like a jump to yourself loop. But this, I guess, is like, we got nothing. Just wake me up when I got an interrupt. Maybe it saves power, maybe it doesn't. Infinite loop to keep the CPU in the halt state. Wait, why do I gotta do this? Why do I gotta keep halting? Something tells me the interrupt is gonna, when we resume from the interrupt, it's gonna point me right here. So that's why we gotta do it, probably. Something about ending our interrupt, like when we asynchronously diverge code, like our code execution goes suddenly over here to handle an interrupt, we gotta go back at some point, and probably it just automatically or naturally goes back here. Okay. Rather than like automatically going back to this halt state. Okay, new keyboard ISR. So this is my code. This is what I want to do whenever someone does something, I guess. So we're saving some registers because we just aggressively diverted control and we're going to go back. So probably we want to save some state. We'll roll with that. These are probably the registers I'm going to use in this interrupt, so we need to save them so that I can restore them. Read the scan code from the keyboard controller's data port. Call handle key press. Okay. Acknowledge the interrupt by sending an EOI to the programmable interrupt controller at the end of interrupt by sending an end of interrupt to the programmable. So if I send a hex 20 to port 20, I guess that means we're done. I don't know why you gotta do that. Why do I need to acknowledge the interrupt with an EOI? Like, is it just gonna automatically re-interrupt if you don't acknowledge under some window of time or something? Okay, then we also have this iret-d, which I think, like I've seen, for example, when you do a syscall instruction, that it saves into RCX the address, like the next address in user space to go back to. I'm guessing iret-d is like somewhere, some register or something has this location saved once it did the interrupt. And iret-d is going to basically get me back here. Probably. That's what I'm guessing. Okay, handle the key press. But why wouldn't it maybe go back here? Like, we haven't finished executing this instruction ever, maybe? But maybe that's not how this works. Maybe it does immediately finish executing the instruction. I don't know. Whatever. Handle key press. Your code to handle the key press goes here. Yeah, so all of that logic. Original ISR. Okay, I don't know if we really care about saving the original ISR unless we were thinking maybe we're going to restore the original ISR. Oh, what the heck is this? Did we ever do this? Setup pick. What is this? I don't remember setup pick. It's a lot of code for something that I think I'm seeing for the first time. Okay. What is this? And why does nobody reference setup pick? I mean, this is set up where it'd be right after the boot signature. So it's possible that this is just supposed to exist at some hard-coded address. But let's see. Okay, also let me see if there's any questions or thoughts in chat. No questions or thoughts. Keep on rolling then. We are deep in the interrupts. In the context of x86. Wait, did I didn't get my explanation from before either. Oh, this. Wait, did we have it before then? Yeah, we did. Okay, you're correct that if interrupts are already disabled, because we had this question, we never read the response. Correct that if interrupts are already disabled, it may seem redundant to disable them again. However, doing so ensures that no interrupt can occur during the critical section of code. So I think it's just like a formality. It's like, okay, I just want to make it clear to the programmer or someone that might read this code later that we definitely need to make sure that interrupts are disabled for this piece of code, regardless of the fact that it's already disabled. The double check provides additional safety. Yeah, exactly. It's almost like a comment, even though it is real instruction. In case you accidentally did something above that code that re-enabled them, now we're re-disabling them. In fact, that's actually, we're kind of acknowledging that here with this, right? This whole block of code needs to happen without interrupts. So we disable interrupts, we re-enable them. Really, we could just delete this and recognize that our current state is such that it's already disabled. And then later on, we basically are doing STI before we hit this main loop so that our interrupts can happen, I think. Cool. Yeah, so it's mostly just a comment thing. Save original. Don't think we need to save things either, because I don't think we're going to ever restore them. Okay, this though I am curious about still. Why acknowledge the interrupt with an EOI? In the context of x86, the PIC is responsible for handling hardware interrupts. When an interrupt is received, the programmable interrupt controller signals the CPU, which then calls the appropriate interrupt service routine, which I think is literally just the fact that there is a code address at some specific location in memory. We get this like interrupt thing that just means jump code execution there. After the ISR completes, it's essential to acknowledge the interrupt to the PIC to signal that it can continue handling further interrupts. Okay. I guess probably if you don't do this, if I had to guess, if you don't do this, you're kind of almost like in a state of CLI where like there's no interrupts ever again because you haven't acknowledged the current one. So how the heck are you ever going to get another one? Because otherwise you can imagine like getting interrupted while you're in the interrupt routine, which can't happen. And I guess it automatically will not happen. It's almost like there's an implicit CLI here or something, maybe, possibly, which means you can't spend too much time in your interrupt because, or at least until you do this. But what happens if we got another interrupt? Okay, IRET D must also be saying you can have your interrupts back. Because otherwise, what happens if I got interrupted while I was in this code here? Like this would be a mess. Well, I guess we did push. So we would just enter here again, push, 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 do this. So technically, but then it could come back and repop. I don't know. Maybe you could have nested interrupts. Unclear. Or maybe this thing also takes care of saying you can have them again. Maybe we should ask about IRET D. Disable. Okay. The CPU executes the ISR. Acknowledge. If you do not send an EOI, the PIC will not acknowledge further interrupts of the same type. So maybe a different type can still happen, which can lead to the system missing important interrupt events. In your ISR, you send the EOI by writing 2220, which is the command port of the master PIC. Why setup PIC is not referenced? The setup PIC procedure is defined in the code to initialize the PIC, but it appears that it is not being called. The setup procedure is necessary to ensure the PIC is correctly initialized and to unmask the keyboard interrupt. Complete example with and to unmask the keyboard interrupt. Okay. Oh, so we do call setup PIC before we do this. Is that there before? I just missed it. No, it definitely didn't have it. Okay, ChatGPT thinks we do need this setup PIC. I think we can get rid of saving this stuff, though. I don't think we care about saving stuff. Also unclear that we need to set up a stack. Well, we do need a stack because our interrupt handlers need a stack. I don't think the stack can be pointed right here. I think that sounds pretty dangerous. Why? Is our stack also going to live at 0x7c00? Isn't that where my code is? Also, do I need to save the original ISR if I don't care about it? That. Okay. So we still have to figure out what the heck this setup pick does. Is used to ensure that the pick is properly initialized. EOI. Okay. You're correct to having a stack at 7. Okay, so we shouldn't have our stack there. So this ChatGPT may have been a little bit confused about deciding to put the stack there. It has decided that this is a nice open piece of land. We're going to go there just to make sure we don't have virtual memory pointed at. Scared of this. No, this does not collide with this either. And hopefully no other hardware is looking there. Okay. Okay, I see a whole bunch of comments that I missed. Interrupt handling routine. The interrupt handling routine is a specialized piece of code that handles the interrupt request for a VGA device. This routine might contain instructions to send commands to the graphics hardware, such as loading an image into video memory. State restoration and return. After the interrupt handling routine completes its task, it restores the program state from the stack and executes an interrupt return IRET instruction, which returns control to the program that was running before the interrupt. Yes, I think I agree with that. Relocating the stack. Okay, so we're gonna go here. And I guess we're making space for our stack, right? Stack segment goes here. We're specifically gonna go to the top of that thing. Yeah. Would it really be, don't we need to like make sure this thing's aligned or something? I don't know if FF is really gonna work. We will see. Removing the original ISR as you do not, yeah, so we don't need to save that thing. Ascent. Okay. Okay, what is this setup pick thing? This is gonna do some sort of stuff. Start initialization sequence in cascade mode. Okay, 11 goes into AL. So we're writing 11 to 20. So this is the master pick command port as we talked about, whatever the heck that really is. But we've learned that at least that thing is also the port that we use for acknowledging the interrupt. If we send 20 to 20, that acknowledges the interrupt. I guess if we send 11 to 20, it sends ICW1 to it. I don't know what that means. Send ICW1, so 11. Also, instead of not just 20, we're also going to go to A0. Send it to the slave pick command port. Whatever that means. Set the vector offset. 20 goes to AL. Okay. So now we're writing to 21. Master pick IRQ 0 through 7 is 20 through 27. Okay. What the heck does that mean? What the? We're gonna need way more clarification on this. This looks like mumbo jumbo to me. Set up cascading. 04 goes into AL. Tell the master pick that there is a slave pick at IRQ2. What the heck does this mean? Tell the slave pick its cascade identity. Okay, so for AL, so we're not only are we writing 20 to 21, and then so this and this are close, right? And A0 and A1 are close. So clearly, I guess this is like 0x2 is like master, and then 0xa is, I guess, slave, but then the 0 1 and then the 1 1. Okay, and then now we're writing to the master pick that there is a slave pick at IRQ2. Okay, so clearly is this like int 0x20 the same as like this 20? Are these things related? And then in this range, there's also like 21 and this 21? Or is this a different range? Tell the slave pick its cascade identity. So 4 goes to 21 and then 2 goes to A1. Why? Set picks to 80, 86, 88 mode. 1 goes to 21 and A1. Okay, so something tells me this particular sequence means some things, and something in here also does a little bit of configuring. Like, is this like, it says start. So this is like the start, and then this is like complete-ish? No, maybe this is complete. I don't know. Unmask the keyboard interrupt. Read the current mask from the master pick data port. Clear bit 1. Okay, well, bit 1 was the thing that gave us the status thing for the keyboard, right? In from 21. What were we reading from? We're reading from like 64 though, but this bit right here is the output buffer status. Is this bit 1 like the same as this bit 1? So we read it in the current mask. We update it by making sure that that lowest bit is a 0, right? That this is just the low bit is a 0, everything else is a 1. So we're zeroing out that lowest bit, and then we're returning it back, right? We read in, we return it back. Okay. Okay, we just need way more explanation here. Okay, this I need way more info about. It doesn't really make sense. Let's see here. We might even need to prompt ChatGPT that you're gonna have to explain this to me like I'm 5, because I really am not getting this. Okay, this like ChatGPT is a little laggy. It's because there's a search, maybe because there's a search. Okay, certainly let's break it down. Pick initialization. The PIC is responsible for managing hardware interrupts in x86 systems. It needs to be initialized and configured to handle interrupts correctly. The initialization involves sending a series of initialization command words, ICWs, to the PIC. Here's the detailed explanation. Start initialization sequence in cascade mode. Edge triggered. ICW1 edge triggered. Cascade and initialize the PIC. I feel like this still is not clarifying. Okay, here, maybe this. Begin the initialization sequence and specify the operational mode. Okay, so we had a 1, 1. Yes, 1, 1. Bit 0. Okay, so this is a bit thing. Good to know. This 11 that we're writing is a bit thing. Bit is like a bit flag, whatever thing. Bit 0, ICW4 is needed. ICW4 will be sent. Bit 1. Okay, so we only have bit 0 and bit 4 turned on. That's not... Why does this think that there's 3 bits on? I don't think there's 3 bits on. Cascade mode? Call address interval. 0 means there's an interval of 8. Level triggered, edge triggered. 0. Edge triggered. Okay, so this is like a hardware concept that I feel like I'm familiar-ish with, right? We've got like edge activations versus like if you look at like a waveform, like a square waveform, it's like, do you do it on the high or on the low? Maybe that sort of world of stuff. Bit 4 initialization. 1 initialization command. Okay, this still doesn't really make sense. Set the base interrupt for the pick. ICW1, ICW2, ICW3. ICW1, ICW2, ICW3. What is initialization command word? Okay, so in each of these, we're writing to a master and a slave, and then that, master, slave, ICW3, ICW4. So we're like sending 4-ish commands to this stuff that's just configuring the hardware to do things, I guess. As in like the hardware being the CPU and how it deals with interrupts. CW2, set the base interrupt vector for the pick. Begin the... Okay, so I think this is just like initializing the interrupt stuff. Okay, and then this is saying where is the interrupt vector, which I think probably the interrupt vector is like, okay, now where are we storing these code pointers? Master pick value hex 20. Slave 28. Okay. Ports go to 21 and A1. Master pick. Oh, this is 20 is the command port. 21 is the data port. Okay, so we have a command port. So this is like what we've got a command. We're instructing you. We're about to do something. Now let me tell you what I'm instructing you to do. This is the data. Yeah, I think that's it. I think we're like, all right, begin a command. We're going to instruct you to do something. So we're writing to the command port. Now I'm telling you what the heck I'm instructing you to do. So we're writing to the data port. Okay, we're going to assume that's what that means for now. I think that sounds pretty convincing. Set up the cascade identity and connections between this stuff. So for master, okay, so we're saying the interrupts for IRQ 0 through 7 are going to be at 20, IRQ 8 through 15. I guess we have different types of, can we only have up to like 16 types of interrupt things that we're facilitating? We only get 16 types of interrupts. Is that what each of these is? You can specify you get an interrupt, you get an interrupt, you get an interrupt, but you can only have 16 types of interrupts. Initialization command word 3. For slave pick at IRQ2. Master pick value. Slave connected to master IRQ2. Okay, so here's the base interrupt vector. Now connect them, I guess. Command word 4. And then we're writing to the data port again. So I guess we have like 3 arguments to this thing, kind of, sort of. We don't write to, no, we write to 21 again here. Okay. Set the base, cascade identity and connections. This is just some sort of bit thing. 4. Like this is just this bit versus this bit. Sure. Set the operational mode of the pick. 86 versus 88 mode. Okay, don't know what that means. Enable the keyboard interrupt by clearing the mask for IRQ1. Read the current interrupt mask from the master pick data port, hex 21. Clear bit 1. Yeah, so this part I think kind of sort of maybe made sense. Procedure initializes the PIC to handle hardware interrupts correctly by configuring it with a series of commands, ICW1 to ICW4. Why is this not considered an ICW? I guess we're not writing to the slave one. But isn't this... Aren't we writing to the data port? So this not... Why is this not considered an ICW? Includes setting the interrupt vector offsets, specifying the cascade setup, and setting the operating mode. Finally, it unmasks the keyboard interrupt to enable handling keyboard inputs. This process is essential for ensuring the system can handle and prioritize hardware interrupts problems. So this is also somehow doing a prioritization of our hardware interrupts. Okay. Why is unmasking not considered an ICW? What the heck what does it mean to be an ICW? It's not considered an initialization command word because it is part of the operational control of the PIC rather than its initialization. Starts the initialization sequence and sets up basic operating parameters, edge/level triggering, single cascading mode. What is single versus cascade mode? Let's ask, what is single versus cascade mode? Defines the master-slave relationships and the IRQ lines. Explain what the heck an IRQ is more. What is this idea of 80, 86, 88 mode? After the PIC has been initialized using the ICWs, its operation can be controlled and modified using operational control words, OCWs. These commands are used to mask or unmask specific interrupts, set priorities, and perform other runtime configurations. Controls the interrupt mask register, which enables or disables specific IRQ lines. Controls the end of interrupt command, priorities, special unmasking interrupts. Example, unmasking, clear bit 1. Reads the current interrupt mask register from the master PIC's data port. Oh, so this bit 1 is not what I was saying. It is not this. Bit 1 is not this. Bit 1 just means IRQ1, thereby unmasking it. So we're like enabling IRQ1. Somehow we must have... How does IRQ1 connect up to... What's it called? How does it connect up to... like this thing? Our new ISR thing. Okay. ICW is used to initialize the PIC, which ICW is used to control and modify the PIC's operation after its initialization, such as masking, unmasking. Okay, I still don't understand the setup phase. Maybe we don't need to understand the setup phase. Okay, single versus cascade mode. In single mode, only one PIC is used. This mode is simpler and sufficient for systems with fewer than 8 interrupt lines. Okay, maybe we need to get out of cascade mode because I don't think we need complex. We just need simple. Cascade mode involves using 2 or more PICs in a master-slave configuration. One PIC acts as the master. Okay, maybe I'm going to ask it to switch us over to single mode. I don't think we need these. We don't need more than 8 right now. I don't even know if I need... I think I only need 1, right? Just want 1 for the keyboard or something. An IRQ is an interrupt request. An IRQ is a hardware signal sent to the CPU to indicate that a peripheral device needs attention. Okay, this is our interrupt request query queue, or that's the queue, like a data structure queue, maybe? I don't know. Hardware signal sent to the CPU to indicate that a peripheral device needs attention. This makes sense, okay? We generate an event. We've got an event, this abstract idea of an event, and it goes over an IRQ line. So somehow we're, I assume, associating IRQ lines with pieces of hardware. I don't know how we're doing that, but somehow we're connecting an IRQ line to a piece of hardware. When a device generates an interrupt, it sends a signal on its assigned IRQ line. So somehow we got to assign it, a device to an IRQ line. The PIC prioritizes and sends the interrupt request to the CPU, which then executes the corresponding ISR, right? Okay, that makes sense. So we want to say like keyboard is this IRQ, which basically means run this interrupt service routine. Hardware does thing, set the program counter to this address, the instruction pointer to this address. Okay. Operating mode of the PIC tailored for the 8688 processors. PIC behaves in a way compatible with these processors' interrupt handling mechanisms. Is the PIC like not part of the CPU? This, I guess it's maybe not. Is the PIC not part of the CPU itself slash CPU architecture? Is the PIC like a piece of hardware? Maybe that's why I'm also slightly confused. I guess this PIC thing might be a piece of hardware, just like the keyboard's a piece of hardware. Instead of, you know, doing fancy things with the keyboard and learning how to read data from the keyboard, we're interacting with this piece of hardware, the PIC. I think that's what this is. Okay, that's good to know. The mode ensures proper interaction with the CPU's interrupt vector table and the way the CPU acknowledges interrupts. Connecting IRQ1 interrupt vector table. The interrupt vector table is a table of pointers to ISRs. Okay, this makes sense to me. We got this table in memory, just a bunch of code pointers. Located at the beginning of memory, 0x0, blah, 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 blah. That's the segment. This offset into the segment, same segment to this offset of. Okay, each entry in the IVT is 4 bytes long, right? It's just a code pointer consisting of a 2-byte segment and a 2-byte offset. Okay, this makes sense. Mapping IRQ1 to vector 9. By default, the PIC maps IRQ 0 through 7 to interrupt vectors 0x08 through F. Okay. So wait, why do we even need to configure it? Is it already set up to do what we want it to do? IRQ1 keyboard maps to interrupt, which is the next one in here. IRQ1 occurs, the PIC signals the CPU, which then looks up vector 0x09 in the IVT to find the ISR's address. Did I even need to configure this PIC thing? Is it already just default configured how I want it? Your code modifies the IVT to point vector 9 to your custom ISR. Well, why? I don't get that. Okay. Do we... Hey, let's ask this. Let's see if there's questions also, or statements in here. Not seeing any. Cool. We'll just keep on rolling then. This is, you know, we're getting very deep in lots. I would like to write some code, but I feel like I need to understand what the heck the ideas surrounding this stuff is before I start writing code. Just like get a good conceptual framework of what's going on here. Like, I didn't know that this PIC thing is a piece of hardware, maybe, right? Programmable interrupt controller. It's not originally part of the CPU itself or its architecture. It is a separate hardware component. It interfaces with the CPU to handle interrupt requests from peripheral. However, the integration of the interrupt handling it's evolved over time with the EU. So maybe it's like now built into the CPU, but we still look at it as an external thing. But like, you know, physically it's, you know, rolled out in the CPU itself. In early, the PIC was an external component. Okay, this thing, it definitely was. Over time, functionality is integrated into the chipset or even the CPU itself in modern systems. Okay. Used in integrated pick. Okay. Advanced. What? Advanced programmable. Oh, we have an APIC. An APIC is integrated and provides more advanced features such as support for more interrupt lines and better interrupt handling capabilities. Includes the local APIC for each CPU core and an IO APIC for managing external interrupts. Okay, we're gonna not roll with that right now. The PIC can prioritize interrupts, ensuring higher priorities first. Is the PIC already configured for my IRQ1 to handle keyboard stuff by default? Do I even need to run setup pick? What's the name of that function? Setup pick? Let's see here. The pick is pre-configured to handle basic devices such as the keyboard, timer, and other essential peripherals. Why does it do this jump? Okay, however, the exact behavior can depend on the specific hardware BIOS. Okay, stop doing jumps. Please, ChatGPT. Typical default configuration. BIOS. IRQ0 is for the system timer. IRQ1 is for the keyboard. IRQ8 is for the real-time clock. Other default. Okay, I don't even think I need to set this up. IRQ1's already set up for my keyboard. System, keyboard. IRQ2 is a cascade. So I guess if you get IRQ2, it means, all right, now go check 8 through 15, I guess. Column 2, column 1, LPT or sound. Okay, I don't even think I need to do this. I think it's already set up. Okay, let's start writing code. I'm ready. I think I understand some things. Let's set up our stack. A little bit skeptical about this stack setup, but let's do it. Okay. First thing we're going to do, set up a stack. We'll match our semicolon spacing. Okay, clear interrupts. In fact, I think we already learned that the BIOS in last week, I think we already learned that interrupts are cleared. Well, all right, we'll leave it. We'll leave it. Okay, clear interrupts. We'll just do that as best practice. Okay, we're setting up ourselves a stack. I'm skeptical about this alignment. I think we might have to do like that or something, but let's see what happens. What could go wrong? Okay. So hold on. Before we do this, here's what we're going to do. We're going to copy this because why use git when you could just do copy? Copy bootloader ASM to bootloader dot one ASM. So this will mean for week 1. We're done with week 1 though. We are now on week 2. After spending over an hour and a half reading about stuff, I think we're ready to write code. Now we're in week 2. Okay, now we've got it saved. Let's set up our stack. I'm going to take this very slowly. Make sure we don't mess anything up. Okay, 9,000 here, this. Okay, so in theory, things should still work. Let's just make sure things still work. We set up the stack. No one cares, right? Stack's good. Okay, cool. Our stack, nothing faulted or failed or complained. Okay, I don't think we care about that. So I don't think we care. No, we do care about that. Don't care about that. Okay. Set up the stack. We are not yet ready to enable interrupts, are we? Maybe we are. Set up ISR. Okay, we definitely need to do this. Okay, but we didn't call ChatGPT, get it together. You didn't call setup ISR. but this does look like something we want to do. Let's just do it. Okay. This is how, okay, we got ourselves a stack. Now we're setting up our ISR. We want keyboard ISR. New is not a very good word. I like keyboard ISR. Or even, now we'll just call it keyboard ISR. I feel like that's a good name. Okay. And then we want to say, what the heck does keyboard ISR do? Okay, well, this is going to when this happens, at some point we want to acknowledge the interrupt to, this is like how we end, right? Acknowledge. I don't know how, if I like my commenting scheme. We might need to clean that up a little bit. I'll put this here. Okay, this is the end. And then we return. Before we return out of this though, I mean, I guess we can just do that, right? Why not? Here's what we'll do. Keep it simple. Let's go back to our original program like this, where we have our main loop, which does all this call, jump, whatever. And then we'll just also add keyboard ISR. So nothing will automatically fall through to this. But I think between this and this, we will now, whenever a keyboard event happens, because I think this address right here is set up correctly, I think this is just going to work. I think we should be able to set a breakpoint and see that this happens when we hit the keyboard. And by default, no GDB, things will still just work. Nope. Line 11 has an issue. Someone does not like something. What's the issue? I don't see the issue. Oh, we need an intermediate register. You can't just go straight in. You gotta take your time. Move AX, offset this, AX. Move AX, this, AX. Take your time. Okay. Run.sh. Nope. What's the issue? What is the issue? It didn't change syntax. No, we didn't do that. This is so laggy. Why is ChatGPT so laggy? Cool. Okay. Oh, sure. That looks maybe believable. Get rid of this offset stuff. Okay, offset, is it just automatically? Let's see if that works. It doesn't like AL? Who the heck has AL? Oh, there's an AL dot. I see. Does not support segment-based references. Okay, that's fine. That's why it told us to switch to CS. We want our code segment. Okay, that boots. One question I have though, can I just do that? Or do I need that intermediate thing? That works. Final question, does that work? That works. Let's assume it assembled correctly. We'll have to verify that it didn't take the first 2 bytes out of this and actually use the offset, but actually, can I do offset? Just to be very explicit. Oop. Let's see. Let's let's look at this bootloader.lst code boot code server bootloader.lst. Let's make sure this did not do something weird. 220. Yes. I think that means that this is correct. I think. We'll assume it is correct. Okay, let's run it now. Does our stuff still work correctly? Still works correctly. Now the next question is, are we hitting our keyboard ISR? So we want to break at address 22. 7C22. Right? No. That's the, yeah, that is correct. Are we hitting this address? And then what we'll do is printf here. Then we will debug it. X8i RIP. Oh, just continue. Okay, we are not hitting our breakpoint. If I look at X8i 0x7C22, we get our 20 goes into AL this, I read W. Okay, so we do have the code there. What was the thing I was nervous about? I was nervous about this. Okay, so our interrupts are not hitting. Did we need to fix our data segment? What is info register DS? It is a 0. Um, oh, we never enabled interrupts, did we? Cool. Let's enable interrupts. We'll do it right here. STI, right before our main loop, enable some interrupts. Okay. Is this now going to work? Oops. Okay. I can type. I can't really type. Somehow a T got here. So chance we're hitting our I or Q though, and that's like eating away the Q thing. No. Where am I? How the heck did I get here? What? How did I get here? I'm so confused. For some reason, our code is executing at FF53, which really doesn't make sense. Why would we be at FF53? Okay. Where am I? Okay, I'm right here, which makes sense. This is us getting a character. A T just showed up again. Now we're at FF53 again. Okay, here's what we're going to do. We're going to start it again. We are going to GDB attach. Nope, we are already there. Something's causing us to divert over to FF53, which I don't know who the heck is doing that. I am not a fan of that. Some sort of interrupt is probably happening. Okay, so I pressed keys, but we're obviously broken. If I step instruction, display 8i RIP. So now we're testing. We're jumping if equal. We're getting 64 again. So we're in our loop. We are just forever in our loop. Okay, here's what we're gonna do. I don't trust this loop. Also, though, curious how the heck a T shows up sometimes. See, my T showed up. Someone's writing to memory. They're not writing in a very nice spot. Here's what we're gonna do. We are going to halt, jump, main loop. How the heck did I comment? Command slash. Oh, command slash. What the heck? I don't understand. Whatever. Do it ourselves. Okay, we're gonna halt and then we're gonna loop again. Do we hit our ISR? What the heck is this? Okay, reboot again. Gotta think about how to debug this probably. There's gotta be like a different IRQ or something that's triggering maybe. So we still are here. We're in our busy loop forever. We now need to set a different breakpoint though. 1E. I just realized. Okay, we want to break as soon as we hit 1E. Continue. Fresh. Oh! Okay, we can hit our IRQ. I don't know where the heck we're going back to after. Somehow we end up over here in weird location of memory. My IRET is not doing exactly what we want it to do, it seems. But we are hitting our IRQ at least once. As soon as it hits here, the machine is like dead. Like it probably seg faulted. I don't know exactly what happens when you seg fault in the bootloader, but it's probably not good. Okay. Continue. So if I go here, I pressed A. We get here, and again. Okay, so we are hitting our IRQ, and then, is this where we ended up before? No, we're in like an even different location. We hit our IRQ, and then something sad happens. Maybe we need to not do this. Let's just break there. And then reboot the machine, attach GDB, continue, refresh, A. Okay, so we are in our IRQ. About to put 20 in AL, ship that off to the port. Now we're at 22. We're about to IRET W, which seems to not be going where we want it to go. Wait, maybe it did. What the? We're back where we want to be. And now we're here again. Because I had pressed multiple keys, probably. Let's jump if equal. Jump if equal. Wait, where's my jump if equal? Why is it doing a jump if equal? How did I end up here? Something went wrong. Okay, so initially we were at 1E, which is where I set my breakpoint, to the, and then I was back at 1C, which is right above this. And then we ended up at 2-0 again, which went to 2-2, and then 2-4, and then 2-0, and then 2-2, and then 2-4. Okay, here's an issue. Somehow we went from 2-2 to 2-4. I don't think that should be happening. We should always be returning back to 1E or something like that. Or not even 1E, it should go to 1C. 2-2, then 2-4. That seems like an issue. Is it IRED D? Did I typo something? What is IRED D? How did it fall through to right here? Okay, here's one thing I'm going to do. I'm going to get rid of all of this stuff. Can always get it back. Okay, we're just trying to set up our keyboard ISR. Technically, we also set up a stack. We'll keep our stack for now. Okay, let's run this again. Let's display 8i RIP. Pressed a key. Okay, so we're at the halt. We're at the halt. We're at the halt. Okay, if I come over here and I press an A. Okay, I'm thinking interrupts don't work while we're in GDB, so I gotta continue, or like, you know. Oh, my breakpoint's no longer correct. We want a breakpoint at, yeah, we did also get to land that we do not want to be at. we want to break at 7C1. That. Run it. Okay. Start it again. Continue. A. Okay. Display 8i RIP. Step, step, step. Okay, we're back here. Jump to that. Okay, did I press multiple keys? I must have. But we did briefly come back here. I wonder, okay, here's my current prediction. My current prediction is that while we were running this instruction, we got an interrupt, which meant it came back to here, which means that the next instruction we should go to is here, which means like that would be bad. Basically, we're returning here. I don't think that's good. Here's what we're going to do. We're going to add an instruction right here, which is going to be a NOP. This instruction should never be reachable, okay? Because we always jump back here. But something tells me we're going to end up right there. Which means we also need to add 1 to our breakpoints because we got a NOP now. Okay, that. Okay. A. Display 8i RIP. Okay, so 20, 20, IRET. Okay, we're at the jump now, which means I should go there, but I don't. What the heck am I supposed to do about that? Just not doing control flow correctly. Okay, one hack is to double up, I think. Maybe. I'm not sure that this will even solve our issue, but we'll try it. How many bytes is this jump? 2 bytes. 1.8, 1A. This, GDB, continue, refresh, press A, display 8i RIP, step, 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 step. It's just falling through. Wait, what? It's not even doing my jump at all? 1B. How the heck did we end up at 1B? My jumps are not being respected. What the heck's going on here? Does anyone have any idea what the heck's going on here? I did have halt, right? That is my instruction there, right? Halt. IRET D. Do I need to do this read? If I don't do this read, is on the off chance I really need this read, let's go ahead and do the read. I don't think I should need that though. But let's see if it fixes it. Okay. 60, 20. What is our registers like CS and DS? Shouldn't my CS register be like 7C00? Or no, I guess not. It doesn't have to be. Info registers E. Yeah, okay, that's. I don't think that's necessarily an issue. Okay, out 20 AL IRET W. It also says IRET W instead of IRET D. Is that an issue? Okay, jump. Info registers CS. Okay, CS just changed. What the heck happened here? Okay, that's definitely a thing that makes me very nervous. I don't think we're actually executing right here. I think when GDB says we're executing here, I don't think we're executing here. I think that's what this issue. Why did my CS get messed with? Okay, this is no good. This seems to be our issue. Does IRET W mess with my segment registers? Here's what we're going to do. Why is my CS register changing? Is unexpected behavior entering an unexpected mode? I mean, there was that one piece of code at one point where we pushed all of the segment registers and then popped them. I think if I search for that, push this stuff. But I think it is correct before I do IRET D. Okay, let's watch it one more time. Let's see here. We're going to run it. We are going to close this GDB, display 8i RIP, display XC. Oops, well, we didn't care about FS, but we can monitor that too. Step. Okay, continue. Fresh. Press A. Okay, what the heck's going on here? CS is currently 0. CS is currently 0. CS is currently 0. Step. CS is no longer currently 0. It is definitely the IRET-W instruction that is changing my CS register. Unless GDB is lying to me in some other way. The IRET instruction should be used in 16-bit real mode to return from not IRET-W. What the heck is IRET-W? Should I just IRET? IRET. Let's try it again. Display 8i RIP, display XCS, continue, refresh, press A, step, 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 step. Boom. Okay, that was the issue. Who the heck told me to put a D there? A different instruction. That is the issue. What is the difference between IRET and IRET-D? Well, mistyped it, but hopefully Jippity will figure that out. IRET-D. Is this actually an option F? Maybe that's a lie. IRET instruction. Behavior pops the instruction pointer, code segment, and flags register off the stack, restoring the state before the interrupt. Usage. Okay, take your word for it. IRET D pops the 32-bit EIP CS. So it's just popping more data off the stack. So it probably messed with CS and okay. Wow, what a bug that was. So that, we've got to be very careful here when we write this stuff. So I think we're working now how we want to be working. Get rid of that. Do that. Okay, now let's go ahead and open up bootloader dot move bootloader 1 ASM code server bootloader 1 ASM. Okay, let's restore some of this functionality. What do we want to do now? Now we're like deciding our logic. I think we want this stuff. All of this logic I want. Okay. But now what we want to do is this. Read from the, okay, so we don't need to check the controller status anymore. I think all we do now is this. Oh, we also don't need a wait for key. Okay, we're just gonna do this. Read a scan code from the keyboard controller. And then I think we just call print car. Call print car. Right, so we pull it out of this keyboard controller and then we print it. How do we print it? Well, we move AX into BX. And then we pull this out. Do that. I think, hold on, there's one other thing. I think we want this back. This is making me nervous. Do that also. Okay, now I like it. Okay, so now it's definitely the high byte is 0. We store this into BX. Do we actually even need to do this? I don't think we need to do this. Can we just do this? Let's see what happens. Will it assemble is the first question. Nope. I don't think it likes that for some reason. I think it'll like this though. Don't know why, but that seems to be the case. Does this just work now? Definitely does not just work now. Okay, we want to set up a breakpoint here at 17. Where the heck am I? Okay, something went wrong again. IRET. This looks good, I think. I feel like all this looks good. Oh, wait, we never set up our video memory again. This. We also need this. We need to set up our ES. Yeah. Let's go ahead and do that. So we've got our stack set up, and then we set up our ES. Is this like our extra segment, or what is this again? Hopefully no one else is messing with DI. I think we're probably fine. Run this, run this. Look at that. We now work as an interrupt handler. Wow, that took some time. I think we learned some cool things. Okay, so now we're in a main loop where we're always halting. And if we want to respond to the keyboard, it happens through an ISR. Okay, we zero out. It's like basically the same logic. We just don't need to read port 64 anymore because 64, instead we have our ISR. How do we set up our ISR? Just right here. Does this work? Also, I wanted to check this, if that assembles or not. Nope. It's very particular. Okay. So we're also at the mercy of no one messing with DI throughout all of this, right? So like certain things might need to be saved off into places if we start messing with registers, you know, but this just kind of works. Print a character. Yeah, kind of like this. Okay, so we clear interrupts. Setup stack at 0x9000. We're not even using the stack though. So technically, we might even be able to get away with getting rid. Here's what we'll do. Let's see. If I get rid of this, does this program still work? We might actually need the stack for. Oh, we don't need it. Oh. How does this work? Say die, RIP, info registers SS. Info registers CS. Info registers SP. Okay, it looks like our stack is just automatically over here. X4GX SP. We definitely don't need giant words. Do we even need, how do I do like that? Yeah. Okay. Info or X8I RIP. I want to set up a breakpoint here. Continue. Okay, press A. What is SP? Yeah, SP definitely moved. So before we were at there, I think this, like it talks about how, I think stuff automatically ends up on the stack. How many bytes do we have here? Before we were at F00. A would be 10, 6, 3. I think we have 3. Oops. I think we basically pushed 3 things to the stack. Right, from A through B is here, C, D, E, F, or whatever. 7, C, 1, 4, right? So on the stack, when we hit our interrupt guy, yeah. Okay, so we hit our handler, right? We hit this guy because of an IRQ. And because we set up our ISR by setting up this, blah, 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 blah. We end up in here. When we end up here, the hardware diverts aggressively control flow over here. 3 things got pushed to the stack. We pushed the address we need to return to right here. What else got pushed? I think it told us. The instruction pointer, the CS, and the flags. So the instruction pointer that we need to go back to. So we need to go back to 1.4 after we're done with this. We also got CS, which as we said, CS is just pointed at 0. And that would explain, you know, if we were reading these as 4-byte values instead of 2-byte values, this would all get messed up. This is right here. And then also 246, which I guess is the E flags. Let's document that. I don't know how much we care, but it's kind of interesting. SP Right at SP, right, is just this, yeah. So we'll say at SP is IP plus 0 is IP. SP plus 2 is CS. And SP plus 4 is flags. Is that actually the name of the register? Info registers flag. Is it E flags? I guess it is E flags. Right. E flags. And this calls it flags. Just say flags. Can I do info registers IP? Info registers IP. Now see, oh, that works. You gotta do, okay, what are all of my registers? Info registers. It just calls it RIP. We also have flags. Yeah, okay. So all of this gets persisted so that it can be restored. The architecture automatically does this. Cool. I'm going to call it what ChatGPT calls it. Yeah. So right on the stack, this is automatically there. Turn from the interrupt. We acknowledge it. We return from the interrupt. We're back here. Loop indefinitely. STI, it will just say, yeah, enable interrupts. Just want to document things. Install the keyboard ISR. Cool. I think this all makes sense. I think this really isn't too bad. Does everyone agree? Is there anyone that's asking questions? Let's make sure there's anyone asking questions. We address that. I think this whole interrupt stuff isn't so bad. I think the BIOS, before we were reading a lot about IRQs and stuff, and I think the BIOS just kind of, it sets it up for us so that the ninth one, who said this? The ninth one? Or how is this laid out for us? Someone talks about this. Let's see here. Explain again. Why is it the ninth one? Who set up what's the vector thing called? IRV? Interrupt request vector? IVT? Vector table? Set up the table to correspond to IRQs and such for us. This is kind of a magic address, but I think it's just automatically configured to point there. And if we wanted it to point somewhere else, we can do that. IVT consists of 256 entries. Okay, yeah. So IRQ1 is the ninth guy. IRQ0 is the eighth guy. What are IVT interrupt? What is IVT again? Interrupt vector table IVT entries 0x0 through 0x7. I'm wondering what this timer is also. If we can use that to like print an A every second or something, if we wanted to. Mapped by the second. What are these initial IVTs? Oh, there are things. IVT 0 is the divide error divide by 0 interrupt vector. Debug, so this is debug exception, a non-maskable interrupt, a breakpoint exception, an overflow exception, invalid opcode exception. Where's my seg fault guy? Bound range, bound instruction, device not available. Debug exception, non-maskable breakpoint. Is 3 like if I do an int3 instruction? Yeah, the int3 instruction will make it so it goes to this guy. Cool. Which one handles seg faults? Or seg faults not even a concept? Where does the idea of a seg fault live? Seg fault is typically handled by the general protection fault or the page fault. Relevant IVT entries. Oh, okay. This is keeps spitting out way too much code. Really, the issue is that it keeps scrolling. Okay. General protection fault. Violation of memory protection rules is in protected mode. But I guess we gotta switch to protected mode before we can get these guys. Interrupt vector 13. Did this say that before? We had someone else laying these things out. 13. Wait, what? 0D. But this guy says 0D is for my sound card. Wait, LPT or sound card. Is this an LPT? No, it's a GPF, General Protection Fault. I thought you said the sound card was 0x0D. I don't understand. Apologize for the confusion. Um, hmm. Segment not present. Stack segment fault. General protection fault. Okay, this guy is 0D. It definitely says that this is 0D. Q5. Map to IVT. They're both mapped to the same thing? Map to IVT. Correct ISR. I don't understand. 0 through 7, IRQ 0 through F, CPU. How Can they both be 0x0d? Something doesn't make sense here. I don't know if we need to go down this trail right now. We probably don't. This app is like lagging so bad. IRQ5. External cause. It's really not. They're both mapped to the same IVT entry, 0x0d, but serve. Avoiding confusion. Guess this is where an APIC comes in? By providing more interrupt. I guess they both do go through the same thing. That's insane. You just have to figure out whether there was a page fault. But the pick, I think they do both go to the same thing. Sure, no conflict arises by setting up ISRs. Disable interrupts. General protection fault. So by default, we'll get page faults and sound events on the same IVT or IRQ or whatever. Is it the pick that generates IRQs, whereas CPU exceptions aren't IRQs, but they both go through the IVT? Is that correct terminology? Separation of IRQs and exceptions. IRQ5 is a hardware interrupt typically used by sound cards. It maps to IVT entry D. There's a CPU exception. It also maps to IVT entry D. Why does it keep telling me I'm like confused? Am I not? I feel like I'm not confused. Hardware interrupt pick. When a sound card or LPT generates an interrupt, the pick sends an interrupt request to the CPU, which looks up IVT entry D and executes the ISR that located there. If the CPU detects a protection fault, it generates an exception and looks up the IVT entry D to execute the appropriate ISR. Why this doesn't cause conflicts. In practice, operating systems and well-designed firmware take care to distinguish between these different types of interrupts and exceptions. They configure the ISRs and manage them appropriately. You can set up ISRs for IRQ5 without conflict. Data segment registers. Set up the stack. I'll set up ISR. Sound card. Acknowledge it. This guy. Handle it. Page fault. Handle it. This set up ISR. But he's literally just overwriting the same piece of memory. Right, this one will just take precedence. They were writing the same location in memory. What is it talking about? ChatGPT is definitely on something right now. I'm pretty sure this is ChatGPT. It's leading to confusion here. What's you're literally overwriting 0x0d times 4 for both. Lots of question marks. How is this properly separating them? So this lag is unbearable. IRQ 5 and general protection fault. Absolutely correct. Yeah, of course, I know I'm correct. Typically handled. They both share, but served. Typical real mode scenario, you wouldn't set both a hardware IRQ and a CPU exception to the same vector. How do I get them to point at different things? It's going to do the same thing, isn't it? Yeah, it's literally doing the same thing again. How would I make sure they aren't both mapped to the same IVT? I feel like this is a lost cause. I think ChatGPT is not going to get there right now. Either way, it's pretty cool. We got this working. Maybe. I think we're still in GDB, aren't we? Continue. Continue. Detach. So the next thing I really want to do, as soon as I give up on ChatGPT on this, put base interrupt vectors for the picks so they do not overlap. I think this is going to go back to the near the beginning of this where we were like initializing the pick and sending those, what was it, like IWCs and stuff. Yeah, exactly. This stuff. I think this is how we would get around it. But realistically, we do not care about that right now. So we're not going to think about that. All right. Forget this nonsense. Let's give it our code. Oops. Explain how I can use the timer IRQ slash how I can set up a timer IVT entry like, and just show my current code. Like, can I just write an A every second? Like once a second, automatically write an A. Is this an option? Ooh. Okay. Whoa. This ChatGPT, get it together. This jumping around is not good design. Also, this like lagginess, also not good design. Guess it's just Safari. Probably lagging. Clear interrupts. Set up the stack. Install the timer IVT. Enable the timer. Unmask IRQ0 in the pick. Enable blah 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 blah. Okay. Timer ISR. Okay, we can write to 21. Like the stuff we saw before does this. Clear bits 0 and 1 to unmask IRQ 0 and 1. I think we're already unmasked. I don't, we'll see. How does it, okay, we acknowledge, increment a counter. Sure, but how often does it trigger? Timer. How often does the timer ISR trigger? Is there a way for me to configure that? Depends on the configuration of the programmable interval timer, another piece of hardware. By default, the programmable interrupt timer in x86 systems is configured to generate interrupts at a standard frequency of approximately 18.2 hertz. So that means it happens 18 times a second. Is that correct? Yeah, I think so. Okay. Well, we can work with that. Why 18.2? Why 18.2 and how can I change it to 1 hertz? The base frequency is determined by a combination of its base frequency and the value loaded into its counter register. Is set to hex 1000. Okay, so this is, I think that explains the Y 18.2. I'm guessing this divided by this or something like that does, yeah. So the base for this divided by this, divide these two things, 18.2. Okay, oh, it's okay. We don't even have to ask. It knows what we want. Cool. Good work, ChatGPT. To change the frequency of the timer interrupt, you can reprogram the pit with a different counter value. Right, I want to set this guy to this so that it's 1 hertz. Changing it. Okay, how do I write to this thing? 36. Access mode, low byte, high byte, the square wave. What the heck is this? Counter value for 100 hertz. No, I want 1 hertz. This value doesn't fit though. Um, um, do, 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 do. I don't think it's gonna work. What if I want 1 hertz? Set the counter value. Send the low byte of the counter. Move the high byte into a L and send that. So we're sending 1 byte at a time, it looks like. So can I send a 3rd byte to get a 3 byte value? Is that an option? Do I get to do that? Mode 3 with low byte, high byte access. I need a different access. Yeah, I understand the math. However, the pit is a 16-bit register. Maximum, that means you can't achieve a 1 hertz. Wait, did they say that the default was that max number? Yeah, that's how it's this is the best it can be, is 18 hertz, I think. I think it's on me if I want using software count. Exactly. Like basically, roughly speaking, I can count to 18 and then just do it, right? That's probably what we'll do. Yeah, this thing. Tick count. Let's just do that. Okay, I think I understand. Let's do it. Let's add our ISR. Install the timer ISR, which is going to be this, which is number 8. And we want timer ISR, and we want timer ISR, and our timer ISR. This is also true. We're documenting it for fun. I don't think, like, probably we don't really care about this. It's an abstraction detail that just happens for us, but for now, we're going to be aware of it. We're going to need to acknowledge and return at the end. We also are going to need to store this. Tick count. This is actually valid syntax. So we don't need a word, we just need a single byte. 1 byte. And then, so it's 18 hertz. We should also say ISR. This happens every 18.2 hertz. What we want to do is we want to increment tick count. Can I do inc tick count? Is this valid? A little bit skeptical about that one, but maybe it is. And then can I compare tick count to 18? And then, all right, what does it generate? Okay, can do that. Oh, yeah, right. We would need to say this. Do we decide dB, one word? Well, okay, then we'll go back to a word. Well, now 1 byte. You get 1 byte. My tick is 1 byte. Well, normally we're in 16-bit. We'll live the 16-bit life. DW. Inc word tick count. Then we check if it's 18. Can't just do that directly, so we will move AX tick counts. Compare AX with 18. And then skip increments. This guy goes here. I feel like we always increment. We'll just say continue, which will, oh no, we already incremented. Never mind. It is whatever. We'll call it continue. I like that more. Now we need to do what we want to do because it's less than 18. Wait, we need to also set this to 0 if it's greater than. Call it 1 second. If it is equal to 18, we're going to 1 second, which is going to move tick count 0. Word, okay, we got to zero it out if it's been 1 second. And then also say finish. Otherwise, no. Okay, we are really overthinking this. So what happens when we have ChatGPT write all our logic for us? We forget what the heck we're trying to do. Okay, jump if equal to continue. Otherwise, fall through. We're at 18. Jump if less than to continue. Otherwise, we fall through. We zero this thing out because we're equal to. And what do we do? We draw to the screen. So we will so it just goes off of AX. Yeah. So what we will do, we need this instruction for sure. move AX. So the high part, we want 0x, 0e to make it kind of fun. And then 41 for an A. Okay, now every second, I think we're going to write a fun A to the screen. Boom. Otherwise, I can still type, but every second, we have an A coming to the screen. And this is why we wrote it asynchronously, so that we can have both tasks happening simultaneously. In reality, most of our time being spent is doing nothing, right? We just halt the CPU until we get an interrupt. But every once in a while, an interrupt does happen, whether it's through us messing with the keyboard, right? We type on the keyboard, stuff happens, or every second, or about a second, right? Really, this would need to happen 18.2e, like we could probably make this more accurate. But about every second, we get an A printed to the screen, which is pretty cool. I think that is some cool progress, right? I think we now understand interrupts a bit better. We've learned some stuff, right? I don't know if I need this documented, but we got this happening. We kind of think we know how we could change the hertz of this pick thing, right? This right here, this logic, if we wanted to change our frequency, but we can roll with it. It's fine enough. I wonder where this comes from. This seems like a very random number. Where does come from? And the other thing to realize, right, is eventually, we might have a concept of like a process, and we're going to have processes context switching, and we're going to have, our CPU scheduling work to happen. I mean, this is probably the same mechanism we might use to make sure that a process only gets to run for a little bit of time, and then the next process gets a turn to do some work, and then the next process gets some time to do some work. This kind of like sits at the heart of that, so that we get to asynchronously interrupt and like do some stuff. Pretty cool. I like that. That is very cool. Okay, ChatGPT, speak to me. Also, I think it's laggy because this window is so massive, because I have all this chat now. Where did it go? Why does it keep telling me it's overly printing my code to me when I ask it a question? Okay. IBM PC compatible systems. I guess it's just a magic number, which used a crystal oscillator to generate this frequency. The base frequency is derived from a crystal oscillator with a frequency of 14.31. The frequency is divided by 12. So is this just like physics? Like a crystal oscillator just oscillates this often? What the heck? This is wild. Why is I'm gonna ask. I think the answer is it's something to do with just literally physics. But I want to ask, why is the crystal oscillator doing that number? What the heck is that about? National color burst frequency. What the heck? The analog television standard used in North America has a color burst frequency. What? 4 times the National Television System Committee color burst frequency? What was convenient? I've never seen someone say that this number was convenient. I guess it's convenient though. Divided generates for a pit. Example. Can divide by 12, and now we have our pit. Can be divided by generate blah 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 for compatibility with these standard. Okay, we're just gonna say it is because it is. Because someone said it is, and that's what it is. How the heck? I wonder why I have this blinking cursor here. I think I always did. Might have just changed the color though of it. Okay, I think this is enough for this video. I think we did some cool stuff. We learned about interrupts, get to install them, they're set up, they do their things, we loop, we do stuff, boom, 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 boom. And suddenly, just like that, we are making progress through understanding this. Thank you all for joining. I have no idea what I'm going to do in the next video, but I'm sure there is plenty to further investigate. For example, still haven't figured out how the heck we get past 512 bytes of code. Now, technically, I think we got plenty of space, right? We're not really running into limitations here. If we look at bootloader.bin, look at all these null bytes that we can fill in with logic. You know, maybe we won't move past 512 next video, because why would we? We got all these null bytes. We can still do more fun things. But maybe we will, because, you know, at some point we got to, so maybe we'll decide next week that's what we want to do. Or maybe I'll hit inspiration on this. For example, you know, maybe there's an ISR or something for the network card. Let's see, real quick, we're going to ask, is there an IRQ for the network card? Just as a little teaser, because if it says that there is, I'm probably going to go down that path. But let's see. Also, going forward, we might need to refresh ChatGPT from time to time to clear its history, but make it so we're not stuck with this laggy, terrible display. I think it said yes. I think that's the IRQ3, often used by COM2, but sometimes reassigned for network cards, often used by LPT, but also commonly IRQ10 and 11, frequently used by PCI network cards. Well, maybe we'll want to figure out, A, does QEMU currently have a network card plugged in by default? And if not, how do we plug it in like the most common way for QEMU? And then how do we detect this thing? And is it on COM2? Does it make sense for COM2 to be a network device? Or COM2, maybe that doesn't even make sense. Maybe network cards don't go over COM2, whatever this. I feel like I recognize this, but I don't know what that is. Maybe we'll have to set it up ourselves. Looks like right here, they're assuming IRQ10 for some reason. But we'll investigate that. We'll figure it out. We'll get some packets, maybe. Maybe that'll be the next thing. Kind of sounds fun. Unclear though. We'll leave that as the cliffhanger to see where the heck we go from here. But did I kill the machine? Oh, I did. Either way, we built something very cool. Every second we get a yellow A, and we can type simultaneously. Very cool stuff. All right, I will see you in the next video. Thank you for all of you that decided to watch this. I know there was a lot of reading involved in this as we try and learn some of the terminology and mental framework and stuff going on here. That's just how it is sometimes. Thanks for watching, and I will see you in the next one. Goodbye.